So Association Quantum, we're here dedicated to spread the quantum knowledge. I know some of us are, you already following us, but if you didn't, follow us on LinkedIn, Facebook, and Instagram. And if you have any questions, you can always email us at info@associationquantum.org. Today, we have an exciting presentation from Dr. Joseph Geraci, and we'll be talking about modeling molecular networks using quantum computing. And this event is sponsored by Encore Cloud Natives. Encore de-risks and simplifies enterprise digital monetization, specializing in financial services and compliant industries. They are the fastest path to the cloud. Thank you, Encore, for again sponsoring us. We really appreciate your support and being there for us. So from here, I want to pass on my presentation to you, Joseph, and tell us more information about what's going on in the quantum. So I'm going to stop sharing my screen.
And I'll share mine.
And you'll share yours. One second, I'm so sorry.
It's okay. I'm sure a lot of people are used to this during the COVID-19 presentation season.
Just keeps the anticipation going.
You should see the disasters I've seen.
Yeah?
Yeah, oh yeah.
Anyone hacked your...
Sorry?
Anyone hacked your presentation?
No, I mean like top speakers not being able to get their things to work, and for like very large events, and it's been pretty bad. So everybody, I will introduce myself. So yeah, my name is Joseph Geraci. I'm the CEO of NetraMark Corp. I'm also a professor of molecular medicine at Queen's University. Let me just share my screen here.
There you go, you can do that. Thank you for your patience, everybody.
Sorry, that's not, can you guys see the PowerPoint? Yes,
we can, just put in a play.
Yeah. Okay, yeah, so hi everybody, a pleasure to be here and thanks for the invitation. So as I was saying, so I'm the founder and CEO of NetraMark Corp, and I'm also a professor of molecular medicine at Queen's University. And our mission at NetraMark is we're basically a specialized small data machine learning company, but you know we use everything, and we also use quantum computation as well. And one of our main missions is in understanding the Achilles heel behind disease. And so a big part of this is understanding networks and quantum computation. It's understood that networks, graphs, are one of the things that quantum computation is going to be great at. So what I want to do is I want to take you to a journey. First, my disclosure before we go on the journey. I own shares in several companies that in pharma and in AI. So I want to take you on a journey, mostly non-technical, but with some difficult ideas, but mostly non-technical. There's one technical slide with some mathematics on it, but I'll take you through it just to talk to you about, I wanted to give some of the people here some quantum stuff to go after. And I'm actually going to show you a live demo of how we're able to penetrate into disease states in this novel way, and why I'm so motivated at trying to get systems to do, network computation more intensely. So what is disease mathematically? So almost all ailments, right? Except, if you break a bone or something, but even then it actually affects our networks. We're essentially this, there's very, very complex network. We have this massive network in our heads, our brains, and then we have these molecular networks. And when we think of a graph, you basically think about nodes with edges connecting, the edges connecting the nodes. And what it means in the brain is obvious. It means a signal is correlated between two regions. And then in your body, it's a bit more complex. And what that has to do with is how molecules in your body actually talk to each other. And this is happening constantly. So proteins have to transfer energy. They have to make, these kind of, these cooperations in order for this functionality to occur. So there's always these things talking to each other. And this is kind of the picture I want to give to you. So the way this works is even for infectious disease like COVID, right? Viruses actually infect, they attack very important hubs in our networks. And bacteria is smarter. They actually attack the immune hubs, right? And so, several things can affect our systems. And our microbiome, which is the bacteria that lives inside our brains, in our guts and potentially in our brains, actually influences this network as well. So you can imagine, so my job has been over the last 10 years is to figure out how to understand these networks better, because it changes the paradigm with which we can treat disease. So before I get to the quantum part, let me just tell you, so I started my journey with quantum computation back in 2004, where I was trying to figure out new algorithms for understanding complex systems, right? And then, since then I've done a few degrees in mathematics and also in medicine. Okay, so let's go on this journey. Okay, so we're basically complex electrical chemical networks, right? And so like I said, we want to understand these networks because it helps us treat disease. So what I'm talking about here in this graph is this is actually a relationship between different diseases according to their different biochemistry that's affected. So you can see that that obesity and Parkinson's are related through a couple of nodes. And you can see that asthma and hypertension are related, and Alzheimer's and heart attack are related, right? So there's all these unexpected relationships that we're starting to figure out. And it's going way beyond this. And I'm gonna actually open up that world for you today. Now, one of the ways, so just a bit of math, right? No, without equations, just let's understand social networks a bit. One of the easiest ways to understand these networks is through what we call centrality measures. Okay, so these are ways of understanding networks. What nodes are important, right? And okay, so for example, how long would it take for a node to send information to the rest of the network by passing a signal? Okay, and so this is called closest centrality. And so this measure actually tells you what nodes do you want to actually go after in order for you to most efficiently spread information through a network, right? And this gives you an example, and it's basically a bunch of linear algebra and so forth. And there's a lot of these centrality measures. I've even invented a couple. Now, there's another way, right? There's something called between-a centrality. I've done some work to show that this is important in our brain. And basically what this is saying is that there's bridges between important connected hubs. And so information can transfer between these two hubs, right? So what I'm trying to get you to understand is that there are these methods that we've developed, computer scientists and mathematicians have developed to understand these complex networks. This one everybody knows about, the eigenvector centrality. This is how Google got started. And it's basically saying, hey, you might not be that important, but maybe you're connected to important people, right? And so this is very important for understanding networks as well. Okay, so now on top of all this is this idea of a random walk. And it's just another way to explore a network. So a random walk on a graph. And essentially what a random walk is this is an example of one that I just let run for a while. And what this does is it's very simple to understand. You start somewhere, okay? And then with some probability, you move along an edge on the graph, and then you continue moving. So if you're moving along, for example, a straight line, a graph was just a straight line with nodes with just edges in between, then you can imagine if you start in the middle, you'd hop a little bit to the right, and then you'd hop a little bit to the left, right? And then you'd see that you'll end up with kind of this distribution that favors the middle, right? Because, you know, you're going back and forth around the middle. Now, you can use this technique to figure out some complex stuff like between a centrality, but this is not the way to do it. It's just to show you that there are ways of extracting this information. But this becomes more interesting when we have quantum. Okay, so let me talk to you about quantum computation, just in case there's people in the audience who haven't gone through, you know, quantum computation. So I'm going to give you a brief review that actually, these are slides from my colleague, Alan Aspero-Guzik, who is a professor extraordinaire at the University of Toronto. And he and I met when we were both invited to Los Alamos back in 2006. This is where, you know, they made the atomic bomb, and they invite people like Alan and I to go and meet and talk. And we were invited, we met. And what we were doing then, back then, is describing essentially the future of quantum computation for drug discovery, which is what Alan does now. And I took the other side, which is I want to understand the systemics behind it. So everyone knows about a classical bit. A bit can be in either state 0 or 1. But in a quantum bit, you have some strange situations. So in a quantum bit, you can be in a superposition of two different states. And mathematically, what this means is that you can map it to a position on the surface of a sphere. And we call this the Bloch sphere, right? So essentially what happens is you can encode this information as some probability of being in an up state, for example, and some probability of in a down state. And it actually is not in either state, and not in some weird, you know, hidden state, but actually in both at the same time until you make a measurement. And so what I'm talking about there is superposition, and then there's entanglement, which I'm not going to get into today, but, you know, we can talk about it. Entanglement's very beautiful because it allows you to form very intimate connections between particles at a distance, so you can transfer information. And then, of course, to have a quantum computer, you need to be able to control these qubits. And because of noise, meaning, so the whole thing here, when you think of quantum computation, is that you need this thing to be unitary. This is easy to understand. You don't need to be a mathematician. It just means that you need to be able to go back and forth, essentially, right? It's invertible. And there's some other properties there. And so what happens is things sneak into the quantum systems. There's noise that sneaks in. There's, you know, heat, vibrations, whatever. And this can screw up the system. And so a big part of, you know, what we need to do is figure out how to stabilize these systems. And there's various efforts, including my supervisor, Daniel Lidar, who's one of the world's leaders at this. So look, here's a quantum computation. So what happens is you have 3 qubits here, and 3 bits can be in 8 different states, right? 0, 0, 0, 0, 0, 1, and so forth, right? Tails, 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 head, tails, tails, and so forth, right? So you can think of these as coin flips. And what happens in the quantum computation is that you set your register, and what you do is you put your state into a superposition of all of these different possibilities, and then you start computing. And the way quantum computers work, the real magic, doesn't come from this magic of being able to be up and down at the same time. Really, what's happening is that the amplitudes, the actual probabilities, they can be, in a sense, probabilities, but the amplitudes of the waves, they can be positive, negative, they can be complex. And what that means is it allows the waves to interfere. And so if you design your algorithm the right way, then what happens is you converge, the system starts to converge to an answer that is most likely the right answer. And so the waves interfere and say, hey, this is the one. This is the needle in the haystack I have to find. This is the phase of the state, whatever you want to find here. And what ends up happening is if you do this experiment over and over enough times, and thanks to some statistics like the Chernoff bound, you can say with confidence, hey, I have an answer here. And so this is very beautiful. So this is what is different about this computation. You can actually allow the likelihoods of these different states to collide and to be simultaneously interfere with each other to come up with an answer. And then there's different gates. So the way to think about quantum computation is basically there's rotation gates, there's this Hadamard gate. Hadamard gate just puts things in superposition. right? And basically what you do is you just rotate along this Bloch sphere that I showed you before. You rotate this vector. And then control knots are extremely important. And what a control knot basically means is that if your first quantum bit is a 1, it flips the second bit. So in other words, 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. If this one's 0, it means I don't activate the XOR operation, right? The addition modulo 2, and you just, it stays the same. And these are generalized. You can actually have many of these, and you'll see it in a gate later on. And then quantum Fourier transform is here because it's famous, and Alan loves it, and he uses it for a bunch of his stuff. And here's an example of a circuit that's used over and over. Okay, so let's keep going. Now, quantum random walk. So our usual random walk is you're sitting in a position, and you flip a coin, and if it's heads, you go right. If it's tails, you go left, right? Or in a situation like this graph, you have 4 different positions you can go, and you can run those probabilities and so forth. Okay, so what happens in a quantum setting, okay, it can be superior on certain networks over others, right? And understanding which ones is difficult, but we're going to get beyond that. Now, there's 2 different types of quantum random walks I'm going to get into. There's continuous and discrete, right? And then I'm going to motivate all this and show you some real world examples. So bear with me through the math, okay? This is the hard part starting now, and then it's going to be easy sailing after this. So D-wave uses a type of paradigm of computation where you anneal. It's kind of like a continuous system that tries to find a lower energy level. And then all of these discrete systems, which work the way we imagine computers to work, IBM Q, Rigetti, the Google system, and some really exciting stuff that I can't talk about right now, is coming down the pipe. And so you have these discrete random walks. And all discrete means is that your time is step by step, right? And so what happens with a quantum random walk is that instead of me going one by one and all this, if I don't measure the system, I can spread through this network. I can just spread, I can take many different paths with different probabilities, depending on the structure of the graph, depending on the weights of the edges. So imagine that. A quantum computer is going to be able to simultaneously go through and actually have and be influenced by the structure of the graph. Now, this is very important for me because of the type of networks I deal with. Now, we can't do this yet, but we're getting there. But let's do a bit of math so I can just show you this, okay? So don't get scared here. This is no big deal. Let's start with the continuous time just quickly. With the continuous time quantum walk, what you do is you essentially encode the adjacency structure of the graph that you're interested in as the Hamiltonian. What this means is that the actual way that the network is connected it's easily encoded. And then once you encode it, you use that to come up with your Hamiltonian. And then what these annealers do is the system evolves according to the unitary operator that comes from that Hamiltonian. All that means is the system is moving forward according to some instruction that encodes the graph. And then after some time, you get this probability of what's my chance of going from node V prime to node V, right? And you start to learn about the structure of the graph. And there's a lot you can do here. And some people have actually implemented these things on small graphs on D-Wave. The problem with the D-Wave machine is that you're restricted with the type of, you were always restricted. Quantum computation is still very restricted. But what you're seeing here is that the actual hardware that D-Wave uses is a graph. It's what we call these chimera graphs, which are limited, but there's ways of encoding information on them, and you can actually do this on them, and I did, and it's a lot of fun. It's beautiful. Okay, but now I want to focus on discrete time quantum walks. What happens here is you can't do the ordinary thing that we were talking about before. Can't we just flip a quantum coin and say, oh, with some probability I go this way and this way? You can't, because you lose this unitarity, right, that you need for quantum computation, this reversibility. And I'm not going to get into it. The point here is this. Let me take you through this. When you talk about quantum computation, mathematically you have these Hilbert spaces, which are basically the spaces where the states live in, right? A state, for example, like an electron, can be spin up and spin down. And so these states live in this mathematical abstraction. Okay, here it's easy. What you're doing here is this. We're defining a coin space and a position space, and it's easy to understand what this is. The position space just encodes where you are in the graph. I'm here, okay? And then the coin space encodes where you're gonna go. And what happens is if you do the math right, you can actually end up doing what I talked about before by spreading in a superposition over all of these different possibilities. So you can create a state instead of the other one where you have that walk that I showed you, that very complex walk. What you have is you can actually have a superposition of all the walks. Okay, so that's where magic happens. So this math is easy to understand. If you were to do the matrix multiplication of this operator S on a state that is up and it's sitting on node I on a vertex. So just imagine in your head you have node 0, 1, 2, 3, and then node -1, -2, -3, just on a line, right? Just imagine like the integer line. And position I is 0. If it's spin up, this operator will make you move I plus 1, which means you move to the right. And if it's spin down, you move to the left. Now, these up and downs are in superposition, right? So it means that this movement is in superposition as well. And so what you can do is you can actually go through the system and see how it advances. And so imagine what you have here. So let me show you. So, so we've actually implemented these quantum walks on one-dimensional graphs. And this is a circuit that can do it. This is actually can be done on the IBM quantum computer with 5 qubits. You can actually evolve in this way. And here's the circuit. Don't worry about what the circuit is saying. I just wanted to show it off. Okay, and now if you look at the way the distribution of a classical walk, you can imagine if you're on a line and you're going around 0, the average is going to be 0 because you're hopping to the right and you're hopping to the left. So your average is essentially 0. Here's a little bit of a blip because it's not perfect. They only did it for, 100 times or whatever. But you can see that it follows this trend. On a quantum computer, a quantum walk, look what happens. You actually get something. You get some bias, some structure comes out. And it's because this superposition and this ability to be able to, exist in this, multiple states at once is actually pulling structure out of the system. Okay, so now the hard part's over. So let me just tell you, there's a way to expand this to arbitrary graphs, not just lines, right? And I've created a few tricks to do this, but I'm still learning as well. And I'm betting on new architectures from quantum computers that will allow me to scale this to when it becomes significant to do the following. Okay, so I want to explain to you why I just put you through all that quantum stuff. Okay, besides the fact that we're association quantum and we're supposed to be talking about quantum computation. Why am somebody like I who's been doing quantum computation for 15 years, why am I dreaming about all this graph theory power? And it's because combining the cutting edge hypothesis generation machine intelligence with network theory is what's going to crack open disease. It's what's going to give us our next generation of therapeutics. So I'm going to show you what I'm talking about. I'm going to give you an example. I'm going to take you through a couple of examples of cancer and how we're doing this, okay? So we're going to extract some mechanisms, and then I'm going to explain how we use those mechanisms to create these graphs and what the graphs look like. So let me share my other screen so that I can do this. Am I good? Can people see the NetraMark workspace? I'm assuming. Okay. Okay. So.
Okay.
Yeah. Okay. Excellent. Okay. So this is an AI platform. I'm not going to get into it. There's different apps in this thing, but what I want to show you is the way we can use a special toy in this system called Netra Play to actually understand disease. So to do that, I'm going to take you on a little journey here. Okay, so like any other clustering algorithm, this is not clustering, by the way, this is just a representation of a reinforcement learning. And this is not based on neural networks. This is something else. And you'll see what I'm talking about. So what you see here is the following. You see the scattering of dots here, and each point represents a person. So if I hover over this person, there's the person's name. And these are the genes that the machine learned from all 20,000 gene expression profiles. It learned about these 16. And it did this because I asked it to learn. I said, hey, I have these chronic lymphocytic leukemia patients. It's a really bad disease, but there's a mild form, which is relatively treatable, and an aggressive form, which is more difficult to treat. So what I wanted the system to do is I wanted to learn. And so you can do this with statistics, you can do this with t-SNE, you can do this with trees, you can do this with UMAP, all kinds of methods. But you can't do this. So what this system did is the following. It said, okay, I'm gonna learn about these two subgroups, but I'm also gonna learn about things you don't know, which is the way the patients relate to each other. Are there subpopulations that you don't know about? And so, for example, you can see that the aggressive group actually breaks up into these 3 little clusters. And so what I can do is I can ask the machine to explain itself. I can say, hey, why? Why are you doing this? I'm just gonna assume there's 2. Create insights, and it explains to me what's going on. It says, hey, and here you can see something very significant going on, 10 to the negative 10 with this gene. You can look it up, it's interesting. Okay, but now that you understand that, let me take you a bit deeper. Let's go into lung cancer, where there's this heterogeneity that we've been able to discover that is actually quite impressive. Okay, so again, I'm gonna do the same thing now. This now is non-small cell lung cancer. This group here is squamous cell carcinoma, these blue guys. The machine did a very good job at isolating it. And it can learn from this small data set, which is impressive. And by the way, the methods, the machine learning that's working in the background was inspired by quantum computation, by the way. These are not neural networks, there's none other methods. This is a method that's able to isolate subpopulations through reinforcement. Because when you have smaller data like we get in pharma, you can't ask the machine to make these predictive models from these small data sets. But what you can ask it is to say, can you make a predictive model from at least something, some subpopulation? Can you learn? And so through reinforcement, it's able to do that. So let's ask the machine why it glued together all of these 35 people with squamous cell carcinoma. And let's Google this. So these are not significance. This is a different measure. When you do one loop, it's a different measure. But let's just ask Google what it is. And hopefully it doesn't embarrass me in front of you lovely people. So Google's going to tell me now that that gene is IRF6, which is non-small cell lung cancer, adeno versus squamous cell. Beautiful. So it's very accurate and it can see stuff. But okay, that's great. So now we understand what's driving it. But there's something more interesting going on. These are different perspectives the machine learns about. And in this perspective here, the machine is able to discover that actually adenocarcinoma breaks up into these 2 groups. In fact, there's a 3rd group over here, and it looks like the squamous cell breaks up. And so what it does here is it actually pulls out features, specifically this one, that's very significantly different. So even though the machine agrees, hey, these people are of one type, they're all one type, and I learned what you asked, which is this, I can actually explain the heterogeneity. Okay, so what does that have to do with graphs? Let me show you Alzheimer's disease, and then you'll see what's going on. And then I'll show you, I'll take you through this. Okay, here's Alzheimer's disease. Our Netra AI's interpretation of Alzheimer's disease is this. These are different perspectives of the same patient population. And in each population, what it does is it pulls out a set of people and it says, hey, this is a pure subgroup of Alzheimer's people, and this is the mechanism. If you look at the mechanisms behind MAP7, if you were to alter the genes in a mouse on these, the mouse would become old within 4 or 5 days. Map number 6 has to do with what doctors already know about tauopathy. Map number 5 has to do with inflammation, right? Different pathways have been affected in different people. Map number 4 has something to do with the gut. Map number 3 is amyloid, right? And so on and so forth, right? So we're currently writing a paper on this now. So what we're doing is we're cracking open disease. So I'm going to stop sharing. I'm going to explain why this is important. Let me get back to my presentation. That's not it. Hold on, sorry. Okay. Okay, so can you guys see the PowerPoint again?
Yes, we can. Just
Okay,
press.
great. Yeah, got it. Okay, thank you. Okay, so now what happens is this. Imagine that I automate this process. Imagine now that the machine is able to learn about these subtypes. It cracks open the disease. It pulls out these genes that are driving the various subtypes. And then what happens is we have ways of building networks out of these. This is the circuitry of your existence. And it gets way worse than this. I'm just showing you this because I found this and I thought it was a very good representation. You have this massively complex internal circuitry that drugs work on. This is where drugs work. Drugs work on these proteins. Now, the amount of computation needed to figure out how to, in a way to, without killing a patient, how to drug this network or how to manipulate it through gene editing, which is the future. But where's the fulcrum? Where's the Achilles heel? This requires massive computation. Now I'm going to show you what we've been able to do in this direction, right? So the power that machine learning and NetraMark, in our Netra, this network analysis that we're doing on NetraMark, we built an automatic system that it removes the person. So I showed you a version where a person can come in and interact. If you're an expert, you're saying, oh, I love this. I understand that this is what's driving this subtype of cancer or whatever your specialty may be. But what we did is we built a system that automatically does this. It cracks open the subpopulations. It extracts the genes that are driving these subpopulations. It builds these protein interaction and co-expression networks, and then it does mathematics on it. And we have to use heuristics because it's too complex. It would take the machine years to converge to an answer. So we use these ways of cutting down our efforts. But it's starting to work, and I'll show you an example. We got a data set with super agers. So these are people that have no cognitive deficiency as they enter into their 80s. Very high IQ people and really great. And what we did is we compared them to people that transition into dementia. And we asked the machine, how do we drug these people? And so the machine started teaching us. I never knew about artenomol. You can look it up. It's very interesting. Guanosine 5-diphosphate, flavopyridol, voronostat, valproic acid, bosutinib, actually trials. Sprycel, right, which is another drug, bosutinib. So what it means is that the machine is starting to understand what's actually going on by doing this very special type of machine learning, this explanatory machine learning where you can extract what's going on, and this graph theory. And so this lonafarnib, this is actually being used in Alzheimer's trials now. It's amazing that this is happening. And so we pulled this out of our Alzheimer's data set. Now, the same thing applies. We did the same thing here for aging. And so we discovered these genes, right? You don't have to get into this, but basically, there's mitochondrial functioning that changes as you get older. And glycopan is implicated as a significant driver and so forth. But the most interesting thing is this: MLF2 is poorly understood. People have thought about this thing having to do with aging, but we actually found, the machine discovered it was expressed lower in older people. But look at the graph theory. So we had to cheat in this case because we knew that this NRF1, everybody in the anti-aging community is going crazy about this NRF1. And because we already knew that, we were able to go to the graph and make massive shortcuts and say, hey, what's near? What has centrality close to it? And you can see there it is. There's the gene the machine learning discovered. And this is the validation that it's co-expressed. It works with this drug that's been, this protein that's been implicated in anti-aging. What this means is the following. It means that if we are able to really push the ability to understand networks better, we'll be able to see a lot more of this. This has allowed us to actually make some COVID-19 advances. We did this about, about 2 months ago. And by using actually information that we learned from older patients who are immune compromised, this doctor-to-be used our system, and by using this combination of machine learning and network, was able to pull out IL-4. Now, again, it's the machine's getting it right. It's getting it right. But there's this discussion about, do we use this drug that affects the immune system in this way or this other way? And the combinatorics that's required, the amount of computation required to actually start understanding these things better, is beyond our reach right now. But we found ways to do it. And so I'm just trying to show you that networks are that powerful, right? And actually, this treatment is now being evaluated. So I hope you're convinced. Now, what we're doing, the next thing we're doing with quantum machine learning, I'm just going to tell you about an effort that's being made now. We actually are going to be growing our own little tiny brain, little organelles, as we call them. And what we do is we extract the proteins from these things, and we build these complex networks, like I was just showing you. And what we're doing is, there's an effort, actually, I can't tell you everyone who's involved, but Microsoft is involved. And what we're doing is, we actually have this quantum ready technology. So in other words, if you can do this graph theory stuff on this hardware that we're building, and we get it to work on this, then we're hoping that the quantum computers of the future will be able to implement these algorithms for real. And so that we can start really understanding disease in a sense that we can't even imagine with our current tools. And so I'm done. I'm happy to take questions.
That's fantastic. So let's come. No, can you hear me?
Yep.
Yeah, fantastic. So let's stop sharing the screen, and then we'll go into Q&A. Wasn't it amazing, guys? Please put in the comments below, what did you like, what did you love, and we'll go into Q&As at the same time. Okay.
Well, I see some good questions here.
Perfect. So we have a question. Do epigenetic interface with the results of machine learning?
So that, yeah. So I can see it. Yeah. So that's a great question. So, okay. So epigenetics is the stuff that you do to you as you live. So you alter your DNA. There's stuff we call methylation and all that. And the answer is that we can actually measure methylation, include it in the machine learning algorithms, integrate it, and learn from it, right? So for example, that result I just showed you, it's funny that I think you asked that question before I even brought it up. That aging thing that we discovered recently about MLF2, actually the first discovery was an epigenetic change that happens to that gene. And that's why people were confused. So we're the first team to actually pull it out of an aging cohort. So the answer is that epigenetics can, if you don't control for it, you might be missing something. I think that's the answer to your question. Yeah.
Okay, that's amazing. I think your camera is off because I'm not able to see you, but.
Oh, no, it's on. Maybe the gallery. Okay. No, it's because you have the AQ on, I think. Maybe put your face up there.
No, it's all good. I tested it, but it's all good as long as they can see you. They do not need to see me. Let's go into the next question. I guess you see the Q&As. You have another question from Shivam.
Okay. Hold on. Do you want me to open up? Because I see other questions. Okay. Yeah. Here we go. No, this is good. Yeah. Okay. Okay. Matthew Fisher posits that there are natural qubits in the brain called the Posner molecule. Is there any way to exploit this in the research you're performing? Okay, so I've been invited by this amazing group in San Diego, led by a physician named Eric Veer, who also happens to be the leader of some sci-fi organization as well. And so what we do is we all come together with science fiction writers and artists and scientists in California, where I used to live, so it's nice. And we talk about this exactly. And I'm going to tell you this. Right now, there's no way to exploit this directly, but I have an interest in this, and I'll just give you a hint. I think that maybe I'm not easily convinced, but maybe calcium phosphate, if you want to do some research, calcium phosphate in the brain is actually capable of this type of behavior, of encoding qubits in this environment. And it'd be amazing. Like, I believe that there's some quantum mechanics in nature. I mean, we know it's all over nature. I mean, the sun would be impossible without it. But, you know, there's other problems. So, I mean, I can get into this. The answer is that I think that eventually we're going to start to understand if we can sustain like coherence long enough in a warm system. And once we show that, then it opens the floodgates. So look up calcium phosphate. You might have fun with that.
Amazing. And last questions, because we have to wrap it up. There's another question from the anonymous attendant. Do you see that? You performed this analysis on existing networks, information from large omics debits.
Okay, hold on. Can you inform these analyses on existing network information from large omic data sets? Okay, so what we're doing is the demo I showed you with our technology does include small and large omics data sets. And actually we're trying to, as a professor at Queens, I'm connected to Kingston Hospital. So we're actually trying to do this for COVID. In addition to that, we actually use private data that pharma companies and stuff give us, and also public omics data sets. So we can do all that, yes, and we have our ways of doing it. The quantum stuff is nowhere close to ready, right? The most we can do are very simple graphs right now, right? I'm just hoping that we'd be able to bleed out and do more.
That's amazing. Thank you so much, and for your presentation and for your amazing insights. This was phenomenal. I learned so much, and I'm sure our audience learned a lot as well. Thank you so much for being here. I'm just going to share a little bit more of what's coming up in Association Quantum.
Thank you, everyone.
So Association Quantum is here dedicated to spread the quantum knowledge, and we have webinars almost every second week. So next webinar, we'll be talking about the history of quantum. So join us on the next webinar. You can follow us on Facebook, Instagram, LinkedIn. We'll be sharing all the information there as well. You can find us on the website, associationquantum.org, or send us an email at info@association.org. Thank you again for being here. Thank you much, Joseph, for being here with us and sharing your knowledge. We really appreciate it. Everybody have a great rest of the day or evening. Wherever you are, be safe and be inspired. Bye.
Thank you.